Most engineering teams are building their AI systems on a flat Earth. They use standard RAG, retrieval augmented generation, a method of feeding outside documents to an AI, and store that knowledge as isolated, disconnected chunks of text. Because these text blocks have no structural relationship to each other, the AI has to rely entirely on probabilistic token prediction. It literally guesses what word should come next based purely on statistical similarity, rather than actual logic. For enterprise codebases, this guesswork is disastrous. An AI agent will confidently hallucinate an API, an application programming interface, which is the bridge that lets different software components communicate, and break the build, simply because it cannot see the overarching system architecture. Throwing more data at the problem or expanding the AI's context window only makes this worse. You end up feeding the model duplicate context, trapping it in infinite recovery loops as it tries to reconcile conflicting text snippets. To eliminate these hallucinations, we can't just slice the text into better chunks. We have to change the shape of the data itself. FastMemory changes this by mapping your data as a series of connected points rather than a flat list. It replaces probabilistic guesswork with deterministic mathematical reasoning. We are moving away from a flat 2D vector store and folding that data into a multidimensional relational web. In this new geometry, an AI agent doesn't have to guess the right answer. It physically traverses verified, mapped pathways to locate exact information. This structural awareness allows the AI to navigate your codebase using specific, predefined logical pathways. At level 1 of this C4 architecture diagram, the migration tool bridges a legacy vector store and a FastMemory Neo4j database. At level 2, the migration CLI routes data through a GPT-4o ontology extractor, mapping concepts and their specific relationships. This uses a script called extractontology.py. Instead of just indexing what the text means semantically, this script scans flat text chunks to identify their structural intent. It accomplishes this using the CBFDAE framework, which systematically tags identified nouns into specific structural categories, for example, assigning a role to an admin or explicitly marking a file as a report. Through this automated tagging, we distill raw, unstructured strings into the foundational DNA required to map out a system's true architecture. Once we have that structured DNA, the tool moves it into a persistent Neo4j graph database. This is where the cipher merge command takes over. Cipher merge checks if a pattern exists and creates it only if it's missing. The script scans for duplicate, conflicting text chunks and harmonizes them, fusing them together into a single source of truth node. With the duplicates eliminated, the system then draws relational edges to connect these unified nodes. These edges create strict directional intent. They map out exactly how a specific function produces data, or how a certain access level governs a function. We call this relational structure the golden mesh. It eliminates isolated context entirely, providing the AI with a mathematically verified map of the system's logic. When an AI agent needs to understand how a codebase works, it executes a structural query against this new FastMemory graph. Instead of performing a blind statistical search through millions of tokens, the agent uses a one-hop traversal. It finds the exact answer in a single jump along an established relational edge. This configuration results in 0% hallucinations on structural queries and 30 times faster synchronization via surgical delta updates, which means the system only updates the specific code that actually changed. By relying on verified system topology, an AI's decisions are linked to the specific architecture of the codebase rather than a generic training set. While the underlying FastMemory engine is open source, managing this technology across massive global engineering teams requires serious operational guardrails. That is why FastBuilder.ai exists. It serves as the enterprise governance platform required to enforce these strict architectural boundaries at scale. FastBuilder orchestrates autonomous coding agents like Copilot, Cursor, and Claude against this verified digital twin. It does this using the Model Context Protocol, which is a standardized method for AI models to securely connect to outside data sources. For highly regulated environments, FastBuilder provides necessary enterprise compliance, including HIPAA support, a complete audit trail, and SOC 2 Type 2 certification, a rigorous standard proving the platform securely manages data over time. Migrating to FastMemory and scaling with FastBuilder.ai replaces brute force guessing with a verified map. By enforcing these architectural boundaries, teams can reduce production-breaking hallucinations and verify that new features align with their existing codebase.